Hello, my name is Ali. I'm a fourth year PhD student at the University of Illinois Urbana-Champaign, and today I'm going to discuss challenging bug prediction and repair models with synthetic bugs, which has been accepted at International Conference on Source Code Analysis and Manipulation. This is a collaboration between University of Illinois and Stanford University. So in the beginning, let's define what are software bugs. A software bug is an error that makes a program deviate from its intended requirements. For instance, if you have this average function, and based on these test cases, if you have an empty list given as input for this function, it will throw division by zero exception. But the correct version of this will have an if condition, and that will cause this average function to now pass on an empty list as input. So the process of detecting, localizing, and repair software bugs is called debugging in software engineering. Now let's look at some of the debugging techniques commonly used in practice. One of them is manual debugging, where you can write some print statements in order to keep track of the variables and inputs to your program. The second one is automated debugging, where you use some automated testing techniques or program analysis to write tests in order to see if for some certain test inputs a bug is exposed or not. And the final one is learning-based debugging techniques, where language models are used for uh, like detecting bugs, localizing bugs, and also repairing them. So our question in this work is, are these techniques, like the learning-based debugging techniques, evaluated effectively or not? And can we challenge these techniques in order to see if their performance will drop or not? So let's look at some of the limitations of existing bug generation techniques more deeper. Well, the first one is that they are so saturated because the community has been focusing on the fix4j benchmark for over 11 years now. And there is a potential data contamination here because the recent large language models have been trained on a lot of data, and there's a chance that all these public bugs are already being exposed to them. The second one is these bug benchmarks are simple because they're doing some simple rule-based mutation operators. That's why it becomes easier for bug detection techniques to actually like detect them. And the final one is these bugs are very simple and also being single line. Most of the bugs are only like involve one single line, and it becomes easy for bug repair techniques to repair them as they are not very complex. So the question we have is, can we generate hard to detect and hard to repair bugs to evaluate these techniques? To that end, we introduced BugFarm. BugFarm is a framework for end-to-end synthetic bug generation. BugFarm first analyzes the attention mechanism of the underlying bug detector and the repair model, and then it identifies the least attended locations to inject the bugs, and then it can generate multiple bugs in those locations. BugFarm generates hard to detect and hard to repair bugs. That's why we are able to use these bugs to effectively evaluate existing bug detector and repair models. And this is happening for two reasons. The first one is that these bugs have different patterns compared to the training data of these models. And also they have like similar representation to the correct code. That's why the underlying models have a hard time distinguishing between them. We compared the BugForm bugs with other state-of-the-art bug generator techniques like Liam and Moobert. Here's a higher here's a high overview of the BugForm framework. BugForm has three main components. Now let's look analyze each one of them deeper. So the first one is method extractor. So BugFarm uses a language-specific parser to extract the methods and constructors. We use the Java lang parser because we're focusing on the Java programming language. And so we start by creating a parse tree for each Java file, locate the method declarations, and then extract the methods and their signatures and pass them to the next component. The next component of BugFarm is attention analyzer. The attention analyzer component takes all of the extracted methods from the previous component and a specific model that we want to target. It first starts by extracting the token attention weights and then rank all of these tokens based on their attention in a descending order That's why we call these the least attending tokens. And then using these least attended tokens, we also rank the statements and then extract the least attended statements from our given method. Notice that for both least attended tokens and least attended statements, we use a threshold K. So K is set to 10% in all our experiments. We only focus on 10% of least attended tokens and least attended statements to inject our bugs. Here's an example of how the attention analysis looks like. Given this method as input to our like component, this is the attention weights extracted for this method. And after running the algorithm, this is the least attended statements that were like determined as least attended statement by the algorithm. And these two lines are the lines that we will focus on injecting bugs. The final component of the BugFarm is bug generator. So the bug generator component takes the set of methods and their least attended statements extracted by the previous components, and it then prompts a strong language model in order to generate n different bugs. We further validate these bugs and check for syntactical correctness, and also make sure that the bugs are introduced only in least attended statements. We set n to be like 3 in all our experiments, and we use GPT 3.5 Turbo as our strong large language model in all our experiments. So here is the bug generator example. So remember that we had recognized two lines as least attended statements. As you can see, those two lines are shown here in subfigure A. Other techniques like Liam and Moubert, shown in subfigure B and C, they are introducing their bugs in other statements, but BugFarm is only focusing on least attended statements in order to introduce its bugs. So what it did was it just like swapped the assignment statements between the if and else blocks. So the experimental setup that we use in our work is we compare with Liam and Moubert, and BugFarm generates like around 1.9 million mutants, which out of which like 700,000 of them are syntactically correct, and 434,000 of them are like confirmed bugs, like through re-executing the existing test suites. The models we use for bug prediction and automated program repair are CodeBird, NatGen, Code5, and Code5 Large. And we considered 15 Java projects from the Fix4J as our subject projects. We also did a manual bug confirmation. We sampled like 300 confirmed bugs like through automated test execution. And we choose 97 participants and assign each bug to at least like 3 participants and ask them to label them as yes, they're buggy, no, they're not buggy, and maybe when they're not sure if they're buggy or not buggy. We spent total 290 person hours, and here's the result. We have 143 samples that we extracted like through majority voting. 72% of them were confirmed as buggy, which belongs to BugFarm, 53 of them to Moubert, and only 18 of them to Liam. This shows the how BugFarm bugs are like tend to be more buggy as confirmed like through our human study. We also asked the participants to rate which tools bugs are more difficult to analyze. And as you can see, 41.5% of the participants says that like BugFarm bugs are more difficult and more hard to detect. Here are some research questions that we considered in our study. Now let's go to our first research question: characteristics of generated bugs. So in here, we had like try to analyze what is it the distinguishing points between BugFarm bugs and other existing bug generator techniques like Liam and Moubert. So the first one is BugFarm changes more statements to generate bugs, meaning that BugFarm bugs are more complex because it involves more statements. So as shown in this table, on average, BugFarm changes like over 3 statements, while other tools like Liam and Moubert changes 2.7 and only 2 statements. We also see that BugFarm changes are bigger yet less noticeable than Liam and Moubert. We calculated the Levenstein distance between So for all like BugFarm, Leo, and Moobert, the edit distance, and we see that BugFarm bugs have an edit distance of like 32, Liam has 25, and Moobert has 20. The next research question is the effectiveness of BugFarm in generating hard to detect bugs. So we noticed that bug prediction models have a hard time predicting BugFarm bugs, as shown in this table. So what we did was we took each model, CodeBird, Code5, and NatGen, fine-tuned them on a specific tool's bugs. For example, the first two rows, 1 and 2, shows that the CodeBird model is fine-tuned on MooBird bugs, and then we use it to predict BugFarm bugs and Liam bugs. And whichever one which has the lowest accuracy precision, you recall an F1 score, that's considered a hard to detect bug. So as you can see, BugFarm bugs um, have a 4.49% lower accuracy compared to the Liam bugs when they are both of them are being chosen as a test set. We also uh, use the same models in order to fine tune them on real world bugs, and we see that even when the models are trained on real world bugs, they have a harder time detecting bug from bugs on average, almost in all cases. Our third research question is understanding if bug from bugs are hard to repair. In order to do this experiment, we chose the state-of-the-art fit repair automated program repair model, which uses Code T5 large as its model. And we sampled bugs from Liam Moobert and BugFarm with one, two, or more statements. And our hypothesis is that bugs are considered hard to repair if the underlying APR model cannot repair them effectively. So here is like the number of sampled bugs. So in total, there are 200 samples. So Liam has 174 one-liner bugs, 25 like two-liner bugs, and only one bug which involves multiple, like more than two lines. And as you can see, the Fed repair APR model was able to fix 36% of Liam and 49% of Moobert. In contrast, the same model has a harder time fixing bug for bugs. As you can see, on average, like 29% of bugs are fixed from bug for bugs, which is a lower success rate, showing that bug for bugs are harder to repair compared to Liam and Moobert. Finally, we wanted to also study the performance between BugFarm and other techniques. So BugFarm generates its bugs much faster, like around 9.2 seconds, compared to Liam 35 seconds and Moobert 28 seconds. So we also show the end-to-end mutant generation time, which BugFarm is way faster than Liam and Moobert. And we also show the what is like the every like different components time. For example, the attention analyzer, the second component of BugFarm, like it only takes like less than 1/10 of a second, but then most of the time is used in prompting a component of BugFarm. That last component, the bug generator, that's where like most of the time is spent in BugFarm. So now some concluding remarks. In this work, we introduced BugFarm, which is a language and model agnostic tool for synthetic bug generation. BugFarm bugs are unique and it involves changes in multiple statements, and it can generate hard to detect and hard to repair bugs. And BugFarm's bugs are generated way faster, around like 3 to 4 times faster than Liam and Moobert. As part of our future work, we plan to integrate BugFarm with more recent reasoning large language models and measure its closeness with real world bugs. We release BugFarm like publicly, and you can use this link in order to access our tool and use it to like generate more bugs and evaluate existing tools on BugFarm bugs. Thank you very much.